everybody, I'm Kathleen, and we're going to start our presentation. Sorry for the delay. This is about OpenVX 1.2, and you'll see that there's a question mark icon on your panel, and that's, if you click that, then you can submit your questions to us, and we'll answer all of those at the end of the presentation. Also, there's another icon there that's of a little page, and if you click that, you can download a PDF of the slide presentation and also the reference guide for the latest version of OpenVX. We are shooting video of this webinar, so you can have that. You'll get an email at the end of this presentation that tells you where you can go to download that. So I'm going to hand this over to Radha Giduthuri from AMD. He's an OpenVX working group member. He will take care of most of this presentation and introduce our other speakers as well. All right, thanks. Radha, I'm going to hand this over to you.
Hi, thanks, Kathleen. So we have three presenters. Frank Brill from Khronos, he is the chair of OpenVX working group committee. And it's me, I'm from AMD, and Thomas Schwartz from Intel. And we three have been working at the OpenVX working group, and there are a lot more members, but we're just kind of giving a presentation. Thomas will give you a high-level overview of Khronos and what kind of activity that we do at Khronos. And I'll go over OpenVX overview, and then Thomas is going to cover the details of all the features that we released in 1.2 and delve into a lot of the details in there. And with that, let me hand it over to Frank.
Thanks, Radha. Yeah, so I just have a couple of slides overview about Khronos and what Khronos is all about. So on the slide you see here in the center, the main issue or the main goal of Khronos is to be the interface between software and silicon. And we have many silicon vendors who are creating special purpose hardware to very efficiently do things like graphics and computer vision. And the software developers would like to be able to have a single interface to that so that they don't have to write special purpose code for every different kind of hardware. And that's where Khronos comes in. So the idea of Khronos is to have standard APIs that can access silicon. These are at a low enough level that they can take advantage of the silicon that's underneath, but at a high enough level where we're always trying to strike this balance to where things are sufficiently abstract and therefore different kinds of hardware can be executed on. These specifications are royalty-free, and there are conformance tests for companies, typically silicon companies, who implement these APIs so that the user of the API can be assured that they will get similar behavior for a given program written to the API, regardless of the silicon underneath that it's running on. Khronos is an international organization that's open to any company. So if your company may be a part already, and if not, you're welcome to join. So there's a lot of momentum behind Khronos, and there's, as it says at the bottom, over 1 billion people are using Khronos APIs every day. I'm going to go ahead to the next slide. So this is a selection of the sort of standards that are available today from Khronos. You see there's a collection of them, and we'll start. Well, over on the left-hand side, you'll see NNEF and OpenVX input APIs for vision and neural networks, and of course, that's the focus of today's talk. In context, there's a collection of other APIs. If we look at the top, there's a lot of APIs for 3D graphics on the web, both an API and file formats for 3D assets. On the bottom, there's a collection of things for parallel computation so that you can write code for a variety of multi-processor systems. And so OpenCL is the API for that, and Spear and Sickle are sort of descriptions of, well, Spear is a description of the hardware underneath, and Sickle is a system OpenCL platform. And then finally on the far right, we have the graphics APIs, which most of us are familiar with. OpenGL, sort of the grandfather of all of this, and then GLES for embedded systems, and the latest Vulkan, which is sort of a reimagining or rethinking of the API that provides a low-level interface and a lot of control to graphics programmers. So again, we're going to talk about OpenVX on the left today, mostly, with a little touch on NNEF. And with that, I'll turn it back over to Radha for that discussion.
Over to Tamar for real details about what we have in OpenVX 1.2. Let's get started. So let me start by saying, in the old days, graphics was processed on CPUs, and it used to be very slow. And then graphic processing was standardized, and we got GPUs and OpenGL, the kind of standards that are the standards that Frank was mentioning in his slide. Now, if you look specifically for pixel processing today, we have many more choices, not just CPU. For example, GPUs can do it more efficiently. And in fact, ISPs are much more efficient than GPUs for doing certain kind of pixel processing. And you may even consider certain custom hardware for certain workloads. But there is no standard way of programming this hardware. Now there's a standard way of low-level APIs to guide the hardware development when it comes to the computer vision neural network workload. And that's what OpenVX is trying to address here. And it's going to basically, it's a low-level API that is designed to make the core applications portable, not just functionally portable, also performance portable. By performance portable, when we say performance portable at Khronos, we mean that it tries to get you the performance, the best performance that a hardware can get. How do we design APIs to do that? That's what we kind of constantly work towards. Now, programmers don't need to worry about how an API is implemented. It's up to the device manufacturer to take care of that. And we do that really by the key feature here we can look at is computational graph. So an application basically expresses their workload as a graph, connecting a bunch of nodes together with some abstract object, and then hands it over to underlying OpenVX implementation. And then vendors take that graph and try to optimize it for more. So I'll cover some more about this graph processing further. But before, I want to mention a couple of the problems that we try to solve at Khronos. Or one of the problems that I'm going to mention here is going to be, I'm going to use the neural network workflow end-to-end to see what are the existing problems and how Khronos is trying to address them. So let's start by, let's say, if you want to train a neural network, you pick a data set, pick a structure, and then there are a lot of choices to pick a training framework. Now, I think if you Google it, you'll find more than a dozen of them. I just listed a few of them here. And you pick one of those frameworks to train a neural network, and you pick corresponding hardware. At the end, what you get is a trained neural network model. And now it may take a week or days, depending on what kind of complexity and how big your data set is. And once it's a kind of offline process. Once you have the model ready, then you want to be able to deploy that into a real system. Then you have to make a decision of what hardware you put, or what kind of hardware, what set of different kind of hardware vendors that you're going to pick, and what kind of inference engine you're going to pick to be able to take this trained network and build an application on top of. Right? And this is one place where you kind of see a lot of players here. There are several deep learning frameworks, which is done by multiple players, and there's a lot of hardware vendors who have different kind of hardware architectures trying to address the same problem, trying to solve the same problem with that. And one place where Khronos is working is OpenVX, trying to standardize the API between application and neural network inference here. You're specifying an API there. And other place is neural network exchange format. This is for the trained. Once you train a network, you want to be able to export all the weight and the structure into a format that can be accessed by multiple different hardware vendors. Right? So I'm going to look at the problem some more in detail. So now, it's the same thing. I'm going to put it in a different perspective. Imagine you're an application developer and you want your application to run across multiple hardware. Now, each hardware have provided their own inference engine that is very well fine-tuned for their hardware. Now, application has to know every API of all the for different inference engines, and also they have to figure out what is the underlying programming paradigm they have to use so that they can map their calls according to that particular API. That's one problem, which is a toll on the application developers. Another problem is now that you have dozen or so deep learning frameworks and there are multiple different inference engines. Now, how do you transfer this data that's coming from training framework to different? All of these are one of these inference engines. You can just see kind of many-to-many problems here. If you try to look from a new framework, then you have to make sure you export it to all the inference engines. Or if you look at it from an inference engine, you're a player on an inference engine, now you have to think about I have to import it from all these different deep learning frameworks. Now, how can we solve this problem? Again, OpenVX tries to standardize the interface between the application and the inference engine. And NMEF is trying to say, well, whatever format, whatever tool you use, you export finally into NMEF that all these inference engines can take. And OpenVX will be able to import these weights too. And not just the inference engine and application and frameworks. Now, there could be some kind of third-party tools that somebody can use to further optimize using just one format instead of trying to support n different formats. Now, let's see. Let's go a little more about OpenVX now. What does OpenVX contain? One thing OpenVX tries to do is abstract underlying hardware. Now, one of the key part is the memory. And OpenVX has memory objects which are used to abstract various kinds of memory usage in computer vision applications. If you try to look at a vision, you tend to have images, you tend to have pyramids, you tend to have arrays, and you also have, if you're using neural network, you have pyramids, you have tensor objects, and they all have certain attributes that are specific. So what OpenVX does is try to abstract all these objects so that application can simply say, I want to create an image with this particular format and this dimensions. In addition to memory objects, now we need certain kind of predefined functions so that every vendor supports those functions. An application uses a certain function, it is ported across all the hardware. So OpenVX does have functions in image processing, image filtering, feature detectors. They include like Gaussian filter, the flashing filter, can-edge detector, Harris detector, fast, hog, template matching. Tom is going to cover more details about those. And then there is neural network. We try to focus on CNN functionality to be able to deploy it mainly from an inference perspective, not learning perspective. It has a couple of other features such as control flow. You don't have to run different graphs, so you can be able to express decision making within a graph. Now, OpenVX is primarily a C API, but it was designed with object-oriented design in mind. So you have all these data objects. They can all be casted to a base object called reference. If you try to go more look into details, you can kind of see that kind of a model exists. And in terms of execution model, we support both synchronous and asynchronous. That means you can give a graph, ask it to just run the graph, and it can wait there, or you can ask it to schedule a graph and do some other processing in the application, and when it's all done, you can say, wait for the graph to complete. Now, in addition to just having using the standard predefined, if an application has certain specific function, little function that they want to do in the middle of doing the computation that is very custom to their application, we have an API to be able to extend, create a user node, and being able to insert it in the middle of the graph so that every hardware vendor will just invoke that functionality when it is needed. Now, let's try to look at the graphs some more. So here is an example of a graph that you can think of. It basically has an input as a RGB image, and output is kind of rendered output, which kind of puts tracking points in there. So the way to start it is kind of define what are your inputs and what's an output. And then you kind of decide all the nodes that connect from input to the output. You kind of place them in a graph, and you connect them using some kind of intermediate buffers. In this particular example, you can see YUV frame, gray frame, array of key points, and there are pyramids inserted here. So once you kind of build a graph like this, you hand it over to a framework, OpenVX, and say, okay, I'm done building my graph, prepare it so that you can execute it over time. That's when an implementer gets the full control of the graph. They try to see how can they map this graph onto the underlying hardware, what are the optimizations they can do, how can they use different hardware. I'm going to go over the details in the next slide about it. Right? So there are 4 key ideas that we used when we were building this API. So we get the best every vendor can leverage taking a graph and try to map it down to their hardware. So the first one is being able to schedule the graph. if you consider a hardware vendor that have multiple different functional blocks like CPU, GPU, or some dedicated functional hardware, they should be able to look at the graph and split the graph into pieces. And okay, I can run this node on, let's say, GPU, or this particular node on CPU because it's very sequential in nature. And a underlying hardware might also look to see whether they want to optimize it for fast execution or low power. They could make those decisions based on whatever the functional profile that they have, the goals that an application specifies. Now, memory management is another big thing. And now, if you try to look at a traditional programming model, let's say if you're trying to build a computer with an application using OpenCV, you have to allocate all these buffers. Application has the burden to reduce the memory by itself. In OpenVX, you can specify the memory as intermediate buffers as in virtual objects. But basically, you're telling the OpenVX that these are all intermediate objects. I'm not going to access them. Underlying OpenVX can allocate the buffers wherever it is. In fact, it can optimize to the extent that it can just use a local memory that is not accessible to the application, or sometimes you can go to the extent of keeping it as a register local memory. Now, the moment these are intermediate buffers available, now application can try to allocate one chunk of memory, try to reuse it across the whole graph. Right? This kind of reduces burden on the application, and a lot more optimization techniques can be done, which are the hardware vendor is more familiar with than an application developer. Now, kernel fusion is another area where if you have a lot of functions that are there, for example, one example I gave is if you're trying to process a Harris corners on an RGB image, you need to first take an RGB image, you need to convert that to some kind of an intermediate format like grayscale, and then you want to that has gray color like by UV, and then extract the luma plane out of it. You want to do a Gaussian filter. In implementation, you look at all these three and say, I can choose all of those into one node that I have. My Gaussian filter can just have RGB, calculate R, and then perform the whole output. So all those things are possible, and implementation can do. You can also use it to do, if you have an OpenCL kind of implementation, you can fuse all of them into generating one OpenCL kernel. And there are different techniques that every vendor uses, and an application doesn't have to worry about it. Data tiling is another technique that we use. Now if you try to process one frame at a time, every time pulling the whole data into the local cache and try to flush it out, you might not get best throughput coming out of the cache memory outlet. So you might choose to say, I'm going to take a chunk of my input image, try to process the graph as much as possible, and then take next chunk, go to the whole graph as much as possible. That way you're kind of making use of the locality in the of the memory in the cache as well as the local memory. These are some of the techniques that people use, and I'm sure a lot of vendors have a lot more techniques than these. Now, let's look at a simple example here to just go over. I just took a simple edge detector, and you can kind of see the code on the left and the bottom. You have a same application drawn in kind of picture. You can see I as an input and O as an output. All these ellipses S, M, and T are different kind of nodes, like Sobel node and magnitude node and a threshold node. So let's look at the graph and how you see it. The first thing you do is you declare your inputs. Now, in OpenVX, you have VX image, which is an abstract object for representing images. You specify what is your input dimensions and output dimensions. You can even specify that format. Is it an 8-bit image or a 16-bit image? Here, for this sake, let's assume it's an 8-bit. I did not have all these parameters, but you can look at actual spec to see the actual formats that you can specify. Once you declare your inputs and outputs, you need to declare your intermediate buffers. If you try to see here, you have H, V, and M, which are basically horizontal and vertical, and the magnitude images that is coming out of the Sobel and magnitude. And once you have these intermediate buffers declared, you basically create the nodes into the graph. So in the first one is Sobel, basically takes the input and produces horizontal and vertical. And then there's a magnitude node, which takes the horizontal and vertical as input and produces a magnitude. And there's a threshold node, which takes the magnitude, compares every value with a particular threshold. If it is greater than the threshold, the output will be like 255, saying Y. And if it is not, it will be 0. So this is the kind of a graph. Once you build a graph, first thing is you have to compile the graph. That means that's where you call VX verify graph. You're telling the underlying OpenVX to check, to do all the checks to make sure the graph is all okay. And that's a placeholder for every vendor to look at the whole graph, try to do all the optimization techniques that I expressed in the previous slide. And this is where they could do the whole fusing. And for this particular example, most of the vendors can just fuse all the 3 nodes into one. They should be able to, without having to go through the external memory so many times. And these virtual objects here, they could all be just registers internally, depending on the implementation. So once you have the graph compiled and verified, you can basically call the process graph or schedule graph and wait graph repeatedly. The goal always of the spec is so that applications can build and verify the graph. Once they build and verify the graph, the process graph runs really fast. That was the key idea here. Now let's go back and look at the OpenVX Evolution to say, we released OpenVX 1.0 in October 2014. And we have several vendors who have implemented, who all have conformant implementations. You know, by conformant means, I think what Frank was referring earlier is, there are certain tests that Khronos provides, which basically tests to see these functions. Are these functions available? And when they're available for certain functions, it also checks to see if the accuracy within certain limits. That's what we check for conformance tests. And we have a lot of implementations that you can see on this slide. And we released 1.1 in 2016, and people are still implementing those. You can see some of the conformant implementations here. And what we did in 1.1 is kind of enhance some more node functionality and cleaned up a lot of the graph frameworks in there. You can also see there is an AMD open source implementation. If you're curious about how an OpenVX can be implemented, you can just, it's on GitHub, semi-license, you can just click there and play with that code. So this year at Embedded Vision Summit in May 2017, we released OpenVX 1.2 release, and we have added a lot of functionality into it. That includes, you know, conditional execution, some other feature detectors, classification, and some more image processing operations. Tom is going to go to the details of it. And we do have a neural network extension. And in order to get the safety critical, we added an import-export function, which I just called it as save and restore here. And those are the functions that's what 1.2 had in here. And along with, at the same time, we released safety critical also. That corresponds to 1.1 spec. I have a separate slide I'm going to talk about. Now, going forward, we are currently working on the next release of OpenVX. What are some of the things that we're discussing? Is one is being able to import. Once the NMES is out, we're going to look at to see how can we import that format into OpenVX. And also provide a mechanism to for applications to specify their own functionality in a mechanism to accelerate on certain kind of underlying hardware. As part of it, we're also looking at OpenCL and OpenVX interop. That's one feature. And in addition, there is also a lot of requests coming from being able to accelerate multiple launches of a graph, being able to support pipelining and real-time streaming applications. We're looking at those. And there are a lot of other use cases we're looking at, such as SLAM and all that. You'll see those features in next year release that we're going to have. Now going back to safety critical, we designed it based on 1.1 specification. Typically, the safety critical always stays one step behind the real spec because we have to do a lot more checks on the specification to make sure every function that we released is very deterministic. Because safety critical systems do require that kind of feature. And also, we identify every feature by number. So somebody who wants to make a safety critical system, they can just checkbox. They can build a test for each of the features of OpenVX, and this kind of simplifies the job. The goal here is to so that we clean up the header file and identify all the requirements so that somebody who wants to take their application with OpenVX underneath, they can save a lot of their development resources to do that. So also one thing we did as part of doing this is basically split the whole OpenVX functionality into development and deployment feature set. In safety critical, deployment feature set is what you're going to actually use in a real safety critical. A lot of graph building features are not needed in there. So what we did is we just kind of remove those from deployment feature set So the way the workflow works is, somebody builds a graph and tests everything, and then they export a binary out of the graph into some kind of a blob, which is kind of vendor specific. In a safety critical environment, the application that runs the safety critical, all it does is just imports a graph and being able to execute the graph, set an input buffer, run the graph, and kind of that kind of a loop that goes in the real safety critical. This reduces number of features that an application, safety critical application developer has to worry about, and that reduces a lot of overhead. And we try to make sure we pass all the missassy warnings. We cleaned up everything just to make things easy for the safety critical users here. Now, this is just one slide kind of going further about the import-export that we came up with. A couple of features in addition to the safety critical here is the fact that you can do development offline. That means you don't have that real-time constraints of just-in-time compilation issues. So there's no constraint on resources that you could use. So you could do offline compilation and try to get the best performance out of the graph, and then you just kind of deploy that in a real-time scenario. Here is a slide that compares between OpenVX and OpenCV and OpenCL. This is a loaded slide. I'm just going to mention that one thing is OpenCL does not have any built-in vision functionality. It's just a programmer tool that people can use. If they want to build their own vision functionality, they could use that. OpenCV is a community-driven. It does not have any conformance test. So if you want to use it on a particular dedicated hardware, it'll be hard to port your application. And OpenVX is a very well-defined API with conformance tests that you could use. I would say we're releasing the slide so you can go each one of these items later after the presentation. So just to close from my overview of presentation, basically OpenVX is kind of you have to think about it as layered architecture. Application tries to express their graph to OpenVX, and OpenVX implementer kind of can map that directly to their fixed function hardware if they have it, or they could use OpenCL or Vulkan or any of their internal acceleration tools to be able to reach out to their programmable solution. Basically, the OpenVX graph abstraction is what enables application developers to express their problem and an implementer to take that problem and map it down to their hardware. So that's all I have from the overview. I'm going to hand it over to Tomer to go over OpenVX 1.2 feature details.
Thank you, Radha. Do you hear me well? So I know that there's no problem. Radha, do you hear me?
You sound great, Tomer. You sound great, Tomer.
Okay. Thanks. Okay, so Radha, please move to the next. To be between the two topics. Yeah, so we wanted to talk first on quantization, because if I'm talking about, now we're going into discussion about the functionality, and there's a big difference between what people are used to when they use OpenCV to when they come to OpenVX and try to run a specific function. It's also in the code what we did in neural network. Is that we do some quantization, and what we have in OpenVX is that we support 8-bit by default, and we extend to 16-bit, and the question is why. So we say that quantization is very attractive in low embedded. Well, first thing, it's very easy to see that it's less bandwidth than float. That means in the term of optimization, we have a benefit of the reduction in bandwidth. We also need less internal memory, and that's power silicon area. It allows very, very low power devices. And also, if I'm looking about the hardware which is doing the calculation, it's smaller as well. So there's big incentive to go and do quantization. The problem with this, the drawbacks with it, it's less accurate. It's not that you did some POC, proof of concept on the float, and then you take this and immediately run it on low precision, it's going to be harder to debug because you lose accuracy, so you don't have bit exact check. And also there is of course there's going to be a degradation in performance in terms of quality, but most of the time we prefer the degradation. Usually the degradation is very, very small, few percentage of degradations. It may sometimes even only one, and the result was so better performance in power, so it makes the actual application possible or attractive. So next slide. So what we did in neural network as an example, we started with Q78, which was a very trivial quantization. We just moved the data from float into int and just clip it. That gave reasonably well performance, but it was not very sophisticated, and it's not quantized enough. So they were working in the literature to go down to 8-bit. One of them is done by Google with GemLOP. They actually did statistic after the training on a specific data set and find what's the minimum value of the maximum value of each input and output of the layers of the neural network, and produce for each one of them separately a quantization formula from minimum and maximum in float into 0 to 255. They also implemented the hardware for that TPU card. Second optimization which was done is int with a dynamic fixed point. There's a tool which is called Illustrator. So all the algorithm is open, and it also does statistics, but it just multiply by scale in order to go from float to int 8, sin 8. There are some more works which are done, but they're like emerging. So it's still not in OpenVX, going into 4-bit and going to binary and trilinear, which is 1-bit or 2-bit quantization. But we take a look at them, and if they've come up into be something which is good enough, maybe we'll add support for it as well. But those methods currently are not to work methods. Please move slide. So what other quantization do we have in 1.2? So we have the OG feature, which are only 16-bit. We have tensor, which are 8-bit and 16-bit only. Also, in the classification extension, the inputs are tensor, and therefore they only accept 8-bit and 16-bit. All image operation are 8-bit or a 16-bit as an extension. Also, template matching accept only 8-bit, although the output is 16-bit because you need enough information. Next slide. So what do we have as new functionality? So we say we have feature detection. I will go a bit more about them later. The OG, the LBP. There's a method to actually compare feature with template matching. It's also compare between images. There's also a function which does line finding, half lines, which is used to do line detections. As we said, we have a classification, which is in a provisional extension, but it works with the spec as currently it is. So you actually import classifier module, which is trained offline, which was done by Cascade or SVM. Well, it does more than just classification. It also detect where the class is. And as I said, it classify and detect where the object is inside the image. There was also more image processing like delayed, rod, median, well, we had them, but we extended them to be more general, and we allowed the radius to support more radiuses. Also, we added the non-maximal suppression, and we also added bilateral filtering to do some edge-preserving noise reduction. And another important thing which we added is conditional execution. In this functionality, we add the node which is doing select by some scalar true or false, and by that scalar which is true or false, we can actually decide whether to do graph, let's say in this picture, graph C or graph B. That will allow more optimization. It also gives us more, well, before that, all those graphs, well, you had to implement in the logic outside of the graph. And there is an ideal which we haven't reached yet, which is to parse everything in the graph, the full workload. So currently, our capability is to actually, the most intensive compute is in a graph, and we need to have some logic on top of it. So the conditional with it, and also put the optimization there, because if you know that you're going to do C, then you're actually not running B, depending on the hardware. And we have many minor improvements. We had the extension of the import and export, the 16-bit support, and the neural network, which we took soon. Next slide. So hog features detectors. So the hog is the histogram of gradient. There's a good example of this picture. In each picture, in each rectangle, you can see that it have a gradient with orientation and magnitude. So this feature is doing histogram of the orientation and normalize them by the gradients, magnitudes, and formulate what's actually this like DNA of what is expressed in this part of the image. What it allows is, of course, template matching. Work on it will work much better, and you can also detect. There's good work on AC, which is ACF, and part of it is HOG, which actually use those features, and later on use a cascade classifier in order to classify pedestrians. Local binary pattern is a very known method. It actually replaced the Viola-Jones or the Haar filter in face detection in many applications. Easily you can see that what it does is compare the pixel to the center, and from that it gives a binary vote. Is it bigger or smaller? So if everyone is bigger or smaller, it's probably a flat place. It's probably a noise. If you see a pattern which 4 are together and 4 are like 1 and 4 are 0, then you probably know you're close to the edge. If you see less, then probably it's a kernel. And if you don't see all of that and you see some random thing, then it's non-uniform. So actually you get something about the pattern of the area which you are checking. Half-line, that's a much more complicated algorithm, but in general what it does is actually finding lines, and it used quite a lot in lane departure warning because it actually sees the line which are painted on the road. If you go to Radar don't see the lines of the lane, so you need a camera, and half-line is doing that. Next slide. Another method which we added is template matching. It used a lot in computer vision. There's implementation to do tracking and object detection. mostly tracking, but also there's if there's lots of noise, then if you know the pattern which you want to see in the image and you look for it in the noise, then you can, after you find it, you can do even bigger noising because you know what is the pattern which you find, and that gives very, very good, very, very strong denoising. Next slide. So the classifier extension, I talked about it a bit briefly before. So what is classification is a problem of identifying which of a set of categories, subpopulation, new observation belong. That means if I have several classes and I want to see, okay, this is a person, or this is a bird, or this is a kite, then you can actually distinguish between the two. Another thing is feature detection, which is also implemented here in this extension, which is the method that I'm to find the bounding box which this class is in. So we made sure that you can implement at least those two methods, which is SVM and Cascade, which is a decision tree. But of course, you can take it to more general machine learning tools to actually implement that classifier. It's very, very, very abstract. Next slide. So OpenVX 1.2 neural network extension, I think this is a big change and a big addition to the standard. So because OpenVX is actually a graph already, and everyone in the industry is using neural network with a graph, that was a nice match. As I said, we just put layers, CNN layers, as actually OpenVX nodes. So from going from one to another, it was very easy. But we needed to add what we say a multi-dimension tensor object between them and not the images we did. So we added those tensors. And of course, we added all the layers with convolution, activation, pulley, full connected, softmax, the convolution. So now we have a capability that you have neural network and you have traditional vision workloads, and they can actually, both together can work in the same graph. So one can actually use vision to extract the beginning of the feature, then run the neural network, network, and then use the result to do something with vision. On another thing to say, because it's also related to quantization, we don't train neural network with OpenVX. We do only inference. This is a major thing to understand. So some nodes are missing because they're used for training, and they are not used for inference. And also, if I take import and export extension, it's very efficient in handling network weights and biases when I deploy the network, but it also gives me a system in which I deploy the inference. This is also a very important feature, that after I train in the lab and I want to actually put it in a real application, I get from OpenVX a real system where I can deploy with an import and export extension. I can deploy it into the hardware very easily. In the future, we'll also enable NNEF files into OpenVX neural networks. Okay, so we made sure that all those networks, Overfit, AlexNet, Inception, GoogleNet version, LSTM, RNN, BioNN, Faster, CNN, FCN, all of them works. ResNet as well, which is not here, but so currently everything we put in it, we found out that we can implement with what we have currently in OpenVX. which is a good thing because it shows that it actually got into a very mature level. Next slide. So we said that we had a tensor object to connect them. So very brief, what is a tensor? Is a multi-dimensional object. So we have a one-dimensional tensor is actually a vector, and the two-dimensional vector is a matrix. But then we use also three-dimensional and four-dimensional object in when we're talking about neural networks, especially when you talk about convolutional neural network. So we added the tensor creation and deletion function, and we also added simple maths for the tensors. We add element-wise, like add, subtract, multiply, table lookup, and bit depth conversions. We also did some transposition of dimensions. In the element also support something which is called broadcasting, that you can actually take a tensor and you know that because it should be the same dimension of the other tensor, and then element-wise you actually broadcast it to the dimension of the second, which the dimension which is missing is a constant, of course. And of course, to be with the spec, also copy tensor patch and query tensors. Next slide. Okay, so what we have in OpenVX neural network extension, as I say, this is a summary of things. We have the int16, Q78, int8, and U8. As I talk about the quantizations. Vendor can support more if they want. As I said, we need algorithm for quantization for that. We also did something, we split it into two extensions. The full 16 and 8-bit support, and only the 8-bit support. So if a vendor wants to support much more lower power SKU, then you can support only the 8-bit. And we also did, when the conformance test, because of the quantization too low, maybe doing some pruning and many other compressions. We did some. We created some tolerance in the conformance test to allow other vendors to do more optimizations. So we said we have 8 neural network nodes, which are their activation, convolution, deconvolution, pooling, normalization, fully connected softmax, and RI pooling. Next slide, which I think it's my last. Okay, so we have this as an example. This is AlexNet's very popular network, and it shows that I wanted to show here the optimizations. So one thing is, one optimization is we can see that it's graph, and we can say, oh, convolution, activation, and pooling, it's better to actually merge them into one. So each box is actually those 3 layers, and if it's possible, then we make it in line 1. Another optimization which we see is we can split it to 2 different executions as the top and the bottom. So you make it parallelism between 2 different hardwares. And at the end, you can see how all this network in total is going. So you have many possibility of optimization here. So thank you. And next slide, I think it's probably Frank.
Yeah, can you hear me now? Hello?
Yes, hi Frank, we hear you.
Okay, great. So this is just sort of a summary slide here, wrapping up in summary for OpenVX. We have this ability to have a fairly quick time to market because the high-level APIs are fairly easy to use, and you don't have to do a lot of hardware-specific development. On the other hand, the graph enables the implementation to optimize for the hardware and do a lot of automatic optimizations for you. And the graph is also abstract enough that it can be portable to lots of different hardware, where not only do we have different kinds of CPUs and GPUs, but also DSPs and FPGAs and special purpose hardware are potentially available. And some implementations do, in fact, take advantage of that. And then at the bottom, you can see some resources in addition to the slides that you're going to get from this and the video that will be available. You can go to the OpenVX website. You can get an overview, the specific specification documents, including the new 1.2. And then there's other resources available for tutorials. There's, of course, the implementations themselves, and that's available at the resources page. Finally, there's a forum page that you can go to ask questions, and we monitor that and try to get back to you in a timely fashion for questions that are asked on the forum. All right, so with that, I think maybe I want to answer some of the questions that have come up on the question. Is that, I guess, the next thing to do here, Kathleen?
Yes. Yes, it is. Thanks.
Okay. So let me just go through at the top here. The first question that was asked was about, it was actually specifically on the import-export extension, and I don't know if, well, that slide, if you'll recall, you create your graph and then you export a binary blob that is then imported in your deployment system. So you can say on a CPU PC workstation, you can build your graph and then export it as a blob, and then in your deployment system, which might be, say, a car, you load it and run it. And the question specifically was, is that binary blob portable? And the short answer is no, because what happens when you go from the graph representation to that binary blob, that compile happens. And it's in that step that it actually takes advantage of the specific hardware that you're going to run this thing on. And so that part is kind of almost by definition not portable because it's using whatever hardware that implementation is targeted for. And so we keep the graph representation itself, and that API is all portable, so it's source code portable. But the binary blob, once you compile it, once you do the verify step, that's hardware specific, and that's sort of that verify step changes you from being portable to hardware specific. So I hope that answers that question. I guess one other thing I'd add is that in addition to being what just source code portable, meaning that you can compile and run the same code on different targets, we have done, I think, a pretty good job of being what we call performance portable, which means, well, it doesn't mean that you always get the same performance no matter what. If you have different hardware with different capabilities, you're going to get a different performance. However, the idea behind performance portability is that without writing any specific code for that hardware, once you do that compile step, you get pretty close to what we would call the theoretical performance capability of that hardware. And it depends, of course, on the quality of the implementation that you have and how good of a job they do in that compiler that when you call to verify. But because this graph is fairly high level, we have successfully done this for a broad range of hardware, including CPUs, GPUs, and DSPs with some special purpose hardware also. So there's implementations out there that actually do a real good job of this. So we're happy with that. So the next question was about, well, it says examples from slides 23 or 22, 23, and 24, and whether they're open source. So I don't know the specifics on those slides, but in general, we have an open source implementation. There's a sample implementation. You can get the OpenVX 1.1 sample implementation from the website here today, and the 1.2 sample implementation, which is probably what's on slides 22 through 24, is a work in progress, and we are basically putting the finishing touches on it and making sure that it passes the conformance test, for example. And so that we expect to release soon. I'm crossing my fingers and hoping to be able to say that it's this month. So it's really fully implemented, and we're basically putting the finishing touches on it. So the hope is that will be released along with the full conformance test package this month. Let's see. So there was a question about making an ARM supported implementation. And so the sample implementation itself has actually been built and run on an ARM platform under Android, as well as the x86 platform under Windows and Linux. And so it works. Now, in terms of there being an optimized version that takes advantage of something you might have on ARM, the sample implementation does not do that. The sample implementation is generally meant to be functional and not necessarily optimized for any given platform. Maybe you should urge your friends at ARM to create an optimized presentation. I shouldn't put them on the spot, but there you go. And so it does work, but there's some more optimization to take care of, say, if you wanted to do neon-type optimizations. That's still something that would have to be done by some particular vendor. Another question is about examples for the neural network extension. And yes, as I said about the other 1.2 features, the plan is that neural networks, there'll be a neural network. I think generally AlexNet is going to be the thing that we're going to show in the sample implementation. So you'll get that. That'll be available. So in terms of the facial landmarks, there's a question about facial landmarks. We don't have anything for that specifically today other than, say, the LBP stuff. But if you're looking for, say, a nose detector or something like that, that's not something that's available now. But if you have some ideas and would like to join the group and see about that for, say, 1.3, we'd definitely like to talk about it. So now there's a question specifically about OpenCL. So there's an OpenCL application running on Windows 10, and they use a lot of float buffers and double buffers. Double, I guess that means double precision floating point, and want to integrate OpenVX. So the question, well, how do we do that? So depending on, I mean, there could be extensions for floating point, but in general, you want to convert your application to fixed point. There's a number of techniques for that. So actually, maybe I'd throw this to Radha a little bit, because Radha has been working with an AMD implementation, and that is in fact open source, as Radha mentioned earlier, and it leverages OpenCL. So, Radha, do you have any comments about the use of floating point and double precision and conversion from that to fixed and floating in OpenCL applications?
So there are a couple of things. If the application is specific to RGB images, we don't have one like that, but we do have a floating point as an extension that we did in our open source implementation. I would say if you want your application to be portable across multiple vendors, if that's what you really look for, I would say you have to try to see if you can map your problem to some of the existing primitives that we have in OpenVX, and then you can make your application completely portable. But if you're trying to get some dedicated functionality that you already have and that is not portable to any of the existing primitives that we have in OpenVX, then it may not be a trivial job. I think it's just that being able to map your problem to existing primitives is the first step. And then if you have some functionality that is missing in OpenVX, then you could kind of post it on the forum, give us a feedback, and we'll try to look to see if we could absorb that functionality. Now, sometimes if the data types are, if you're using something like, let's say tensors, if you want to use our double precision or single precision tensors in there, and we don't have that supported as part of the mandatory spec, but you could, and if you look at our open source, it's still under development. You would see the floats of tensors supported there, but not every vendor is going to be able to support it because they may not be designing their hardware to address that particular need. Frank, I think.
Okay. Yeah, thanks, Radha. So then there's a question about OpenVX on RPI or BeagleBoards. I'm not familiar with the RPI. The BeagleBoard typically runs on a TI device that's mostly ARM-centric. TI does have, in fact, an implementation that has been passed the conformance test for version OpenVX 1.1. I don't know if they've ported that to the BeagleBoard specifically or not, but that's really a question for maybe for the TI guys. I don't think that they have officially supported or released it for the BeagleBoard, but it's certainly something that they could potentially do. And then there's our RPI is Raspberry Pi. Yeah. I'm not aware of any specific Raspberry Pi implementations. I don't know if anybody else on the phone is. If you go back, if you go to the resources page, you can actually see specifically what implementations are available today. There's about a dozen of them, I think, and so, but I don't think any of them are running on Raspberry Pi today. And then there's a question about OpenCL, and yes, the sample implementation, well, it runs on x86, but then there's, of course, the AMD open source implementation that specifically supports OpenCL, so you've got that available. I think I touched on at least all of the questions that are in the question panel here, so I don't know if there's anything else, or I can throw it back to Kathleen. Do you have any advice or closing comments here?
Yeah, if there are no more questions, we'll go ahead and wrap this up. Just a reminder that in probably an hour or two, you're going to get an email from us that will give you the URL where you can go to download this video. And also at that time, we'll have the PDF of the presentation posted there, although you could also download that here. That's it. Thank you so much for joining us. And watch your email when we have other webinars. We'll be sure to let you guys know. That's it. Thank you.